Well, good morning, everybody. Boy, what happened?
What do you mean?
Where's everybody?
Scared of mom?
Scared of mom?
We started talking about differential equations.
Usually what happens is the train is what happens. Well, whenever the train crosses McKinley, gets down traffic for like 10 minutes.
I avoid that.
Yeah, go onto the tracks. That's my advice. Let's see. We've got. I don't know what the lab number is. I want to say 5. You've given up on anything being in order ever again in this class, right? Lab number 5, I think, tomorrow, because we've already done lab number 6, so that makes sense. We have an internal numbering scheme that we use for all the labs, and we didn't want to change all the labels on all the shelves, so we figured this was easier. And that lab is all about Newton's second law. We're going to use frictionless carts on tracks. Oh, I got to show you physics string tomorrow. So yeah, we'll do all that tomorrow. Today, what I want to do is I want to do the example of the banked turn, and then I want to go ahead and get started on chapter 7. Okay, supposed to be starting chapter 7 today, so I'm only a little bit behind, but chapter 7 and 8 will make up time. All right, so the banked turn, right? Oops, no, come back. There we go. I'm gonna admit to you that this one is rather awkward to draw. Okay, so it's gonna look an awful lot like the fact that my Apple Pencil isn't working at all. One second. Wake up here. Are you connected now? Here we go. All right. It's going to look an awful lot like a hill. However, I'm going to do this with my tissue box here, okay? We've got this banked turn, and what I've drawn here is like a cross-section of the turn, right? And what's going on here is the car, right, is sitting on the turn and is driving into the screen. When we had the picture back here, right, of that car right there, see how, well, tell you what, we'll do it driving out of the screen, since that's the picture we've got here. That car is driving directly towards us, right? And so what I'm trying to draw is like I kind of cut into the hill, and I'm doing a freeze frame of the side of the hill. And so when I draw the car, again, the car will be a box, right? And, I mean, don't draw this, but like these are the headlights right there, right? And there's the windshield coming directly. This is a very poor car, isn't it? Maybe I shouldn't draw things like that, right? Because it just looks like a pig from Minecraft. So this car is driving out of the screen, right? Okay? So, you know, up, down, into the turn, out of the turn, and then there's like a forward direction. So this problem is essentially three-dimensional, but we're not going to worry about the coming out of the screen motion, okay? Is there a force that's required to get the car to go and maintain its speed as it goes around this turn? Sure, right? Okay? And so there's going to be friction between the road and the motor force and all those different kinds of things. We're not going to worry about the forces that are propelling the car. What we want to worry about is the forces that are keeping the car in the turn. And so when I sit there and I try to analyze the objects that the car is interacting with, well, I've got the earth, which gives the car its weight. I've got the surface of the road, which is going to cause this normal force. But then I also have friction. And now the question becomes, which way does the friction point? It is static friction because the car isn't sliding. Okay? So let's just step back for just a second and make sure we hammer home this concept and idea of circular motion, centripetal forces, and whatnot. Let's take a ride on the physics bus, okay? I'm going to drive the physics bus, and we're driving towards the front of the room, and you're all sitting in the physics bus, right? Okay? So I'm going along. What I want you to do is move in your seat, okay, in whatever direction I turn. So if I turn to the left, which way do you go?
Right.
You go to the right?
No, two legs.
Which direction is the force on you when I turn the physics bus to the left? Name the objects that are exerting forces on you as we turn to the left. Now, we've got the earth. I give you that, right? So that one's down. You got normal force for the seat on your rear end straight up, okay? But as we turn to the left, which way are you being pulled, and what object is causing that pull? The direction of the turn is to the left, right? Which way is the center of the turn? To the left. What's pulling you to the left? Friction between your rear end and the seat. Okay? But why do you all sit there right now and think, well, it's to the right? Because that's what I experienced, Mr. Bailey. I'm going to do the car, right? Okay? And my friend turns the wheel, I get pinned against the passenger side door, right? Okay? Now, is there a force that pulls you to the outside of the turn? Name the object that is pulling you to the outside of the turn. No invisible demons came along, threw a fiery lasso around you and took you to the outside. No. You can't name an object, can you? And yet, a minute ago, you would have sworn up and down that there was a force to the outside, right? Why do we think that that force exists? It's a fictitious force. It's one we invented. Why do we think there's a force to the outside? Newton's first law. What were we doing just prior to the turn? We were going forward. And now the physics bus is turning to the left underneath us. If we try to keep going forward while the bus turns left, what's going to happen? We're going to run into the side of the bus, aren't we? So that feeling of being pulled to the right, that's inertia. We invent a force, just like we invented the force of we hit the gas at a stoplight, right? Okay, and we accelerate forward, and everybody thinks, "Oh, you push backwards." There's no object that pushes you backwards. The car is pushing you forwards, right? And so these fictitious forces are real. We experience them. But they aren't caused by real objects. They're caused by us changing the coordinate system, basically, to be us-centric as opposed to what's going on. So for this car, in this turn, as it drives out of the screen, in order to be tugged towards the center of the turn, which way does the force of friction have to act on the car? Towards the center of the turn. But the friction can't act out of the surface. The friction has to be perpendicular to the normal force. And so the force of friction is going to be parallel to the surface, but pointing toward the center. All right, what direction is the acceleration of the car? It's going on a circular or portion of a circular turn, right? Okay. So which direction is the car accelerating? inwards, but what direction is inwards? That way or down the slope? All right. If it were down the slope, then the car's motion would be changing in a direction down the slope. Is that what happens when you go through a turn? Driving along, and all of a sudden you just start plowing into the road. No. So the acceleration has to be perfectly horizontal. The turn, the circle, is a perfectly horizontal circle. The car is riding up on the edge, but it's going around in a flat circle. How you doing? Giving up all hope of ever being an automotive engineer now?
Oh, no.
No?
No.
How do you, like, some of you I know are sitting there going, there's no stinking way I ever would have known any of this. Well, now you know. Right? And knowing is how you know stuff. And there's more truth to that than you think. What?
So the acceleration is pointing inwards as well?
Pointing towards the center of the turn, directly inwards. If you try to draw it in the plane of the slope there, then the car has to change its direction into the ground somehow. And that's not what's happening. All right. I've got all the objects. I've got the correct acceleration direction. What are we going to do for our coordinate system?
Make positive x on the A.
Positive x along the A. That's Mr. Balo's rule of thumb, rule of safety, rule of sanity. So that means I'm going to make positive x be perfectly horizontal and positive y be perfectly vertical. In doing that, now that I want to write down Newton's second law in the x and y directions, what am I finding components for? The mg is fine this time. What direction does mg point? Negative y. It's only, that's it. But now the force of friction and the normal force, I have to go find components for. I could have tilted my coordinate system, but then I would have had components of A cosine, A sine. And that has always felt bad to me. So, we're going to have MA in the x direction, but we're going to have 0 equals in the y. Again, that sort of simplifies our math. But here we have to go and figure out the components of F and N. So let's do, I don't know. Should we do N first? So we've got a coordinate system right there. My component of N will stick vertically up and then horizontally over that way. And I think I will draw it up there because it's going to get busy down there in the middle of this block, this car. And then what about F? The horizontal component of F points like that, and the vertical component of F points down. Again, I didn't draw those at the center of the block this time because I wanted to try and see my triangles better and try to make my drawing a little bit clearer, but maybe I didn't. Maybe I made it more confusing. But in order to find out whether they're sine or cosine, I need to know where the angles are, right? Well, a little bit of geometry will show me that that happens to be theta. I know that because of the rule of alternate interior angles. There's two parallel lines, and when you have a diagonal through it, alternate interior angles are equal. And then as I work my way around, I'll also find out that theta is sitting right there. Good. I didn't do that geometry for you because I think you're capable of doing it. So give your brain a break and just trust me on that one. Creepy smile included. All right. So what does that mean for the horizontal component of F? Is it going to be sine or cosine, and how do you know? Cosine, because it's done. This is going to be F sine. And then for the normal force, the horizontal component of the normal force.
It's going to be sine.
That one's going to be sine. Why? It's not touching. And I certainly hope by now you have just given up on the idea that cosine is x and sine is y. Hopefully by now you've seen that sine and cosine will change their definition depending on where the angle is. So I have made you free. Right? You're no longer bound down by these archaic ideas. All right. So in the x direction, oh my gosh, this diagram looks scary, doesn't it? There's just all kinds of garbage in here.
Earlier you were saying the friction was pointing towards the center of the car. Was that right?
When we were on a flat, when I was driving the physics bus.
Oh, okay.
Right? But the friction can never leave the plane of the surface.
Okay.
Friction and normal force always are perpendicular to each other.
Okay.
All right.
I just wanted to
So-
get that straight.
So in the x direction here, what have I got? I've got f cosine theta. This gets really hard. You can really mess up and miss some things if you're not careful. I've got n sine theta. I got that one. And is there anything else? No, I'm not seeing any other horizontal forces. So is f cosine theta positive or negative? N sine theta? Positive. You wanted to put negative, didn't you? But they're both positive. And is that okay? Yeah, we want an acceleration that direction, don't we? So there's no problem if both of them are positive. All right, in the y direction, what have I got? Let's see. Looks like I've got an n cosine theta, an f sine theta, and an mg. So I got that one, I got that one, and I got that. I think I got check marks on all of my forces now and their various components. So n cosine theta, which way does it point? And f sine theta? Negative. And mg? All right, there we go. So there's the setup. We're going to have to remember how fun this is. And then a whole bunch of algebra will ensue. I've taught you about the AMO step, right? The AMO step is a miracle occurred. Right? It's called algebra. And I'm not showing it to you. But what I am showing is the punchline. And it's horrific. Cosine theta all over cosine theta minus mu sine theta. So there it is. The speed at which a car will safely round a banked turn of angle theta with coefficient mu. And how did I get v into this thing? Well, this is circular motion, isn't it? The acceleration is centripetal. And so I can substitute in v squared over r for that acceleration to find that v. What are the implications of this result right here? Because this is just nasty. If you had to try to check this in your head by playing around with angles, your brain would just hurt, right? So let's ask some other questions. Oh, first of all, we could ask what happens when the angle is 0? What happens when there's a flat surface, right? Well, what's the cosine of 0? It's 1. Sine of 0? 0. Cosine of 0? 1. All right. So basically, I'll get mu rg, won't I? Square root of mu rg. So if theta is equal to 0, v is equal to square root of mu times r times g. All right? So what that means right there is we now have the speed that any car can negotiate a turn safely at. For a given coefficient of friction and a given radius of the turn, that's the maximum speed. Because once you go faster than that, there's going to be sliding. That means that for all those flat roads on the East Coast that aren't banked, What happens when you hit a patch of black ice and your coefficient goes to effectively 0? There is no speed that you can safely negotiate that kind of turn. You're going to be going straight, the road is going to be turning. There's going to be no friction. And you are going to end up in one of those nice ditches they have on the side of the road for catching cars. All right, but what if the coefficient became 0, but the angle was not 0? What is my speed going to be then? Well, with a coefficient of 0, I get sine theta divided by cosine theta. Both these terms go away. So what's sine over cosine? It's tangent. And this right here has a non-zero answer. In other words, for a given angle and radius of the turn, there is a speed in which the turn can be safely negotiated. What force, what component of what force is providing the center-seeking or centripetal force that keeps the car in the turn? It's the component of the normal force that points in the x direction, towards the center of the turn. It's the n sine theta. And if it's angle 0, you don't have n sine theta, right? It's just gone. So here, in a banked turn, the normal force helps keep the car in the turn. It means that there needs to be less friction. It also means that you can go faster. Don't do that. Right? Don't do that. Mountain roads, right? Stay under the speed limit. So, lots of physics going in here, lots of tie-ins, some gotchas with the frictional forces and normal forces and things like that. But, this is a fairly general solution here. It does assume that the speed of the car is not changing. It's going through the turn without changing its speed. And does assume that you've got static friction between your tires and the road. All right. Hoi. That was probably a little bit brutal to give to you at 8 o'clock in the morning, wasn't it? But I think it was absolutely necessary. All right. Now what I have to do, I'm going to use an analogy from cars that maybe a lot of people don't understand anymore. Do you guys know what a manual transmission is? Yes. Still? Okay, good. All right. Drive one? Good for you. Yeah. My son is 16. He's expressing interest in learning how to drive. I think we're going to go find a beater manual. Right? But I'm giving up hope because I think by the time he actually drives any amount of time, there's just going to be electric cars with AI Ubers that come and pick you up and take you places. Anyway, what I need to do right now is go from 5th gear to 2nd gear. And for anybody who's driven a manual, right, okay, that can be pretty brutal. It's a lot better than going from 5th to reverse. I'll tell you that. But we got to change gears, okay? We got to think in a different way. And up till this point, with the last 2 chapters, it's been really brutal, right? All these equations, all of these force vectors, all of this math, right? Like, what choices have I made in my life that brought me here? What am I doing, right? I thought I had a handle on the first unit stuff, and now I'm giving up all hope. Let's bring the hope back. Because we want to talk about energy. Well, at least I want to talk about energy, and since you paid to be here, you want to talk about energy too. We talked about mass, and we talked about how it's hard to define what mass is, right? I think if I asked you the question, what kinds of energy are you familiar with? We could probably come up with a list. Shout some out. What kinds of energy are you familiar with? Electricity, thermal, potential energy, chemical energy. Good. Asian energy. Right? Classic Chinese medicine. They talk all about all kinds of energies in the body. The force. That's not energy. I didn't hear nuclear. Nobody, oh, I'm not familiar with that one, Mr. Bailey. Yeah, it's there. So we don't have trouble doing that. But if I turn around and don't answer this one out loud, if I turn around and say, what is energy? It gets a little bit harder. Paul Hewitt teaches at City College of San Francisco. He's a fantastic physics author. He writes a conceptual physics textbook. It's absolutely amazing. And he defined it this way, right? Because mass and energy are related to each other. You already know the spoiler alert on that one, E equals mc squared, which is physics 4C territory. But I really like this definition because it gives you an idea of the roles that mass and energy play. Right? And as we talk about energy, it's going to be a concept and an idea that is going to help us move things around. Objects are going to be gaining energy and losing energy. But I think you already know something about energy that is really, really critical to our understanding of what's going on here. And it's the fact that energy is a conserved quantity. And this, for physicists, conservation laws are how we know that we're doing it right. There are features of the universe that we live in that seem to be built into its very fabric. And this is one of them. The idea of the conservation of energy. What does that mean to conserve energy? Turn off your light. So they've replaced all of our lights. They've replaced all the lights with LED lights and replaced all the light switches with these motion sensors. Okay? And we're finding that, so we've been turning the lights off because our moms yelled at us, right? To always turn the lights off. So whenever we leave a room, we just turn it off. Well, turns out when you turn these off, it like reboots the computers that control the lights. Brilliant design, right? And when you come back in to turn it on, the lights don't know what to do. Like you hit the switch and they'll turn on, and then they'll dim, and then they'll go up, and then they'll dim, and then you go up, and then you feel like you're in a disco, right? As it tries to recalibrate itself. So nowadays they're telling us we're not allowed, we shouldn't be switching the lights off. And so now I'm in a real ethical quandary because I walk through the door and I just hear my mom yelling at me, turn off the light, right? But my boss said I couldn't. So it's not about turning off the lights. What does it mean to conserve energy? We transfer it around. We trade one type of energy for another. But what do we know about the total amount of energy anywhere in the universe? It's the same. Whatever that number is, it's a constant. And we can't get any more of it. We don't make energy. What does a power plant do? It takes one kind of energy, maybe the energy of falling water, and turns it into another kind of energy, the energy in an electrical current. So energy companies, power companies, they don't make anything. They just distribute it really well. So one way to sort of, mathematically capture this idea is to just write down that simple statement, right? Whatever I start with, whatever the initial energy that I have, it's going to have that same energy at some final point. So if I take my tennis ball and I hold it here, okay, it has energy. It has something called gravitational potential energy. And this is getting a little bit ahead. This is chapter 8 stuff, but I think you already know about it. Okay? And if I let go of the ball, what's going to happen to the gravitational potential energy? It's going to change. It's going to go from being stored in the gravitational field to giving the ball some velocity, right? Okay? So let's see if energy is conserved. Let's just pretend. I'm going to make up some numbers. Okay? Let's say the ball has 10 joules of energy right here. And the floor we'll call 0. Okay? So when I drop the ball, how much energy should it have when it hits the floor? 10 joules? How fast is it going? 0. It's at 0 energy, and it's not moving. It went from 10 to 0. I broke physics. Why didn't I break physics? The energy went somewhere. The energy went into forming the tennis ball. It went into the sound that you heard as the ball struck the floor. It went into heating the floor up slightly. It went into the air. So energy gets transferred all kinds of places. If we wanted to talk about the energy the ball had right before it hit the ground, if we're very careful about what we define as initial and final points, then if it had 10 joules of potential energy up here, how many joules of kinetic energy did it have here? It had 10. But then something happened to make that energy go away, to make it seem like it got lost. When you are driving your car has kinetic energy, and then you hit the brakes, and all of that kinetic energy goes away. You come to a stop. Where did it go? It went into heat and the brakes and the sound and all kinds of things, right? When we have an energy loss, and what we mean by that is it changes into a form of energy we don't know how to deal with, we are going to summarize that through a concept and idea called work. So, while that's a true statement, okay, it's not the one that we're actually going to be using. Instead, we're going to use a modified form of it. We're going to put another term on the initial energy side called work other. And what this term is going to let us do is handle all of those lost forms of energy that we can't keep track of. Because here at the beginning, we're only going to keep track of kinetic and potential energy. Later on, we'll add other forms of potential energy. When you get to 4b, we'll add on thermal energy. When we get to 4c, we'll talk about, and 4b, we'll also talk about electrical energy. And then we'll finally get into nuclear energy in 4c and all these other forms of energy. But for now, we're just going to concern ourselves with kinetic and potential energies. So if friction's involved, friction likes to take energy and turn it into heat. Where do you think friction's going to end up in our terms here? It's going to be in that work other term. You might read in your books, this book, and basically any physics textbook anywhere, or if you're reading online, you might hear people talk about conservative and non-conservative forces. Physicists have not become suddenly political. Okay? A conservative force means that the work that is done is path independent. It doesn't matter what path it took. But forces that are non-conservative are path dependent. And what we mean by that is basically friction. Friction is our standard model for non-conservative forces, and it's going to be showing up in the work other term a lot.
So you had talked about when the ball hits and there's some sort of friction, and you said that dissipates the heat.
Mm-hmm. And sound. And changing the shape of the ball temporarily. Yeah.
Okay.
And if I was an engineer, I'd go worry about all that stuff in the work other term. But I'm a physicist, so I'm just going to lump it all together and throw it in there. Somebody has to do it for real. As long as it's not me, I'm happy. All right. So what we've got to do now, so I've introduced that idea to you. We're going to come back to it on Monday. Because what I want to do now is talk about work. And what work is going to do to us is it's going to require us to think a little bit more about vectors. And based on the definition of work, we're going to have to learn how to multiply vectors together. So let's take a look at this, okay? When I say the word work, what do you instantly think of? Calculus. Fair enough. Thank you for not saying physics. Probably your job, making money. Why do I go to work? So I can make money. Why do I make money? So I can pay taxes. Why do I go to work? So I can make money. Right? So work has a lot of connotations, and we've got to be very careful about what we mean by work in a physics sense here. Okay? Work, mechanical work, is what you get when a force causes something to move a distance d. Literally, force times distance. So let's look at these students here that are on their field trip. If that car is neither going up or down the hill, are they doing any mechanical work? No. Why not? No distance traveled. If there's no distance traveled, no work, mechanical work has been done. Are they doing biological work? Yes, right? They're expending energy in their muscles to hold that car up, assuming the brakes are gone, right? Okay? We're not talking about that, right? We're not talking about energy expenditures in organisms or any of those kinds of things. We're narrowly looking at objects, whether or not they're moving, right? If there's no force being applied to an object, then there's definitely no work. But even if there are forces being applied, if the objects aren't moving a distance, there's still no mechanical work that's been done. Am I doing any work on the board? Is the board doing any work on me? Why not? It's not moving? Are you allowed to say that now? Yeah! Oh, finally. Right? Something that makes sense. Yes, if it's not moving, work isn't being done. Just can't be. Is there any work being done? Yes. By my hand on the box? No. Why not? It's not moving. All right. What happens if I push it up? Yes. Yes. Okay. What happens if it comes down? Negative work? I want some of that. What do you mean by negative work? What direction was the force of my hand on the box as the box came down? The force on the box from my hand was still up, but the box was moving down. Why was the box moving down? Because I was letting gravity win. Gravity's pulling the box down, right? But my hand is still holding it up. My hand didn't suddenly turn around and push the box down. So, the normal force between my hand and the box was still up, but the direction it went was down. My hand was doing negative work on the box. All right, let's look at it from the point of view of gravity. Work done by gravity on the box, positive or negative? Positive. What direction was the force of gravity? Down. What direction was the box going? Down. That's positive work. Positive or negative? Negative. Why negative? The force of gravity was down, but the box was going up. Do you see how there's a really narrow focus? I was saying the work done by gravity. Work is all about like a force doing something. You can talk about the network. You can like add all the work, all the forces together and do a distance. You can do that, and you'll be asked to do that. But when we think of the work done by certain things, we've got to be really careful. Work done by my hand or work done by gravity. Look at the directions those forces are going. Look at the direction the object is moving. If they're in the same direction, it's positive. If they're in opposite directions, it's negative. how much work is the normal force between my hand and the box doing? 0? The box is moving horizontally. Direction of the normal force was directly up. The direction and the normal force were perpendicular to each other. To go from positive work to negative work, you have to pass through 0 work. So, when you're talking about a force, and there is perpendicular direction of motion, no mechanical work is being done.
So I have a question.
I have lots of questions.
So if you're holding the box and it's not moving, the moment it starts moving, that's when you start doing work?
Okay, I was talking
So it
about
doesn't matter
the
what-
normal force, the one that was pointing vertically. You're right. In order for me to get the box to move, there's friction, isn't there? Is the friction between my hand and the box doing any work? Yes. The friction is horizontal, right? If I carry it here to the left, okay? What direction is the force of friction? Everybody point. It's in the direction of motion. Why is it in the direction of motion? Static. Right? It's not sliding. So, static friction, is it doing any work? Yes? Positive or negative? Positive. All right, now I take the Kleenex box and I slide it across the table to the right. What kind of friction is it now? Kinetic. What direction did it act? Opposite the motion. Positive or negative work? Negative. This isn't easier, Mr. Baylor. This is harder. So what we do, in order to capture...
Going back to
Yeah.
the kinetic energy.
Go ahead.
Explain why that is.
I'm going to. But we got to talk about work first. So, to capture this idea of work being positive, work being negative, and work being 0, we are going to define a very special kind of vector multiplication. We are multiplying two vectors together. Here I'm using d vector, but d vector could very well be a delta x, a delta y, a delta z. Your book, I think, uses s as sort of a generic symbol for any kind of displacement that's been done. Okay, since we talk about constantly work as being force times distance, I like using d because d is distance. It's kind of how I taught. So even though s is in several books, it's a little bit old-fashioned actually. It's kind of going. If we wanted to be strictly correct, we would use r, but then every student thinks that means radius, and we don't want to go there yet. So, but you'll notice that something is, well, quite frankly, missing on the left-hand side. There's no vector sign over the work. That's because work is a scalar. Work has positive and negative connotation, but work itself has no direction. The force and the direction come together to cause work to happen, but work itself isn't directed in any one particular way. It's simply an amount.
Dot product.
Okay. How many of you have heard of the dot product before? Good. That's how many people have paid attention in their prerequisite classes. The dot product is my friend because it's the vector operation that allows me to get rid of vectors. It's like the ultimate hit squad. It's great. When I'm in the vector jungle and I don't know my way out, I just whip out my emergency radio and say, dot product. Boom, all the vectors just run into the woods. Okay? What happens here? How does it get rid of vectors? Like, this is awesome. Well, we'll come back to that, okay? We need to talk about what this dot product really means. Okay? Now, we're multiplying two vectors together, aren't we? And if I wanted to be really careful, I could write my A vector as, well, in unit vector notation, as the sum of its components. I'm gonna go for the full all 9 yards here. Okay, I'm gonna do 3 dimensions. Don't worry, I won't do any 3-dimensional stuff, but I just got a little bit of mathematician in me every once in a while. It says I gotta show what's going on here. B, same story. And what do I, J, and K mean again? X, Y, and Z. All right. Well, this is a multiplication, isn't it? So that means that if I want to multiply these two things together, let's just pretend I don't know what I'm doing. I would take A, whoops, in all of its glory, and multiply it by B. All right. For those of you that are in a panic right now, B, Z. Okay. Just trust me. This will work out. Don't worry. Okay. Because we're going to do some physics right now. Well, we're going to do some math, but we're going to call it physics. Okay. So I've got two terms there that when I do the product, because each of them has 3 in it, I'm going to end up with 9. Is that right when you FOIL this? 2 by 2 ends up with 4. I think a 3 by 3 ends up by 9 or 12. I don't remember. Okay? That's okay. I'm going to get rid of most of the terms. Because it's going to be AX I hat times BX I hat, right? And then AX I hat times BYJ. And then it's 9. Okay? However, when I do that, I'm not going to do it in full. Okay? But in part, I'll get an AX I hat times a BX I hat. Right? And then I would get a AYJ times AXI times BYJ, and then AXI times BZK plus dot, 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 dot. Right? I keep going, right? Because then I'd start with AY, and I'd march through all those, and then AZ, and I'd march through all those. One of the things you need to understand about the dot product is that it is asking and answering a very specific question. The dot product between two vectors asks this: how much of one vector points in the same direction as the other vector? How many of your math teachers taught you that? Yeah, see, they like to hide stuff from you. The dot product is often called a projection. And when you project onto anything, that's the question you're asking. How much of the thing projects onto what I'm referencing? So dot products in physics say, well, how much of A vector points in the same direction as B vector? If they both point in the same direction, then we would get 100% or 1. If they point in opposite directions, we wouldn't get 1, we'd get -1. It's 100%, but in the wrong way. And if they're perpendicular to each other, 0. Who keeps calling? Reedley College. Fresno City College Physics. Yeah, I think you do. No problem, bye. I didn't want to tell him he was in front of the class. Oh! They hear the word physics and it's like, oh. My worst nightmare has come true. Best way to shut down any conversation. What do? I teach physics. Oh. So, we go from 1 to -1 to 0. That first term right there, AXI times BXI. AX and BX are just scalars. So I would just multiply them together. And that leaves me with I hat dot I hat. And what's the question? How much of I hat points in the same direction as I hat? Answer, all of it. 1. And what's AX, BX, and AX times BX times 1? AX, BX. All right. What happens with this next term? Well, we got AX and BY. They're just scalars. But now I have I hat times J hat. How much of I points in the same direction as J? None of it. What happens in the next term? I and K are together, aren't they? None of it. So if I carry that pattern through, what happens to every term that is not I hat times I, J hat times J hat, and K hat times K hat? It's gone. It disappears. 0. I love the dot product. And in the end, what you end up with are products of just the same components together. All the X oops, that was supposed to be Y's. Otherwise, the mathematicians would really hurt me. What we end up with are the products of the components added together. Take all the X components, multiply them together. Take all the Y components, multiply them together. Take all the Z components, multiply them together. Add all those numbers up. There's no more direction. It is just a number. And it's trying to tell you something about the product of those two vectors and really how much of those products are in the same direction. So that's one way to do a dot product. Again, you don't have to go through the whole rigmarole, right? What you really need to do, if you want to do A dot B, find the X components, multiply them, find the Y components, multiply them, and then add that together. You're done. Another way that you may have seen this defined, and it's no less true, but it is a bit of a trap, is this one. Have any of you seen this one? Okay. So this works as well. And the nice thing about this one is it also captures that whole idea of what happens when two vectors are pointed in the same direction. The angle between them is 0. So what's cosine of 0? 1. So magnitude of A times magnitude of B. What happens if they're at 90 degrees? Cosine of 90? 0. And what happens if they're 180 degrees? Negative 1. So that captures that idea really nicely. But I would warn you to be careful about the angle between the vectors. You got to make sure you nail the angle between the two vectors. What do I mean by that? Well, what if your vectors point like that? If I gave you my pencil and asked you what is the angle between the vectors, where would you draw it? It's got to be right there. Okay? Sometimes I see students try to do that angle or this angle. Those angles don't work. Okay? So that's why I caution you about this one. Okay? If you know the angle between the vectors, go for it. But quite often vectors are not given as the angle between them. It's given as the angle of the vector. And so you've got some geometry to do before you find the angles between them. All right. So what does that have to do with our work terms? Right? Well, work is that dot product. So that means, among other things, that we can find the work by doing F times D times the cosine of the angle between the force we're talking about and the direction the object's moving. You'll see that done quite commonly. For example, maybe you have a box and it's sliding along the ground, like a suitcase or something like that, but the person is pulling with a force F up at some angle theta. Well, the displacement vector is perfectly horizontal. And have they given us the angle that we need in order to do FD cosine theta? Yes, they have. So that one works out really nice, right? So look for situations like that. Now, this probably is not the only force that's acting on this object. There's no doubt a normal force and a weight, and if it's sliding along, there's going to be some friction, okay? But which of the forces that I've pictured here do I need to worry about in this displacement? Friction. Why? Because it's in the horizontal. And what else? What component of the force is the horizontal one? It's cosine. Is F sine theta doing any work? No. Yep. It's the cosine. F cosine theta is... Where'd they come up with cosine? Oh, now I know. My advice to you is to not worry so much about FD cosine theta, but really think about, okay, it's F times D. Which component of the force do I need? Because what would happen instead if the box were moving up? What if we had a force like this, but the displacement was vertical? And you were given the angle right there. You can either go and find the other angle, the angle between the vectors, or why throw away a skill you have bled over? Namely, finding the components of vectors. Find the component of the force that points in the same direction as the distance. That one, sine or cosine? Why? Not touching. Done. Force F sine theta times distance. I'm done. You're like, but Mr. Beta, now it's FD sine theta. I know! That's why I don't like FD cosine theta as a definition. I'd much rather you think about it in terms of find the component of the force that points in the same direction as the distance. That's safe. You know how to find components of things now. Or at least you should. I don't know why physics textbooks do that. They switch chapters and then they ignore everything you've learned up to that point. It's like, just use the same skills. They're all good. All good skills to have. All right. This one, that one works okay as long as your force doesn't change. And believe me, as a physicist, I'd say, you know what, forces never change. I'm good with that. I'll live in my little perfect universe. But you know what? The more interesting things happen when you start looking at forces that do vary. And so, for the first time in this class, we are going to start talking about when things change.
This might be a little off, but I have a question in regards to sine and cosine. So if we're trying to figure it out and cosine 0 doesn't work, so you suggest just use sine 0?
No. You have to take a look at the direction that the object is moving and the force that points in the same direction and the angle that you've been given. It's not always going to be neat and straightforward. Yeah, don't fall into the trap of thinking that one always work, which is what FD cosine theta does. It teaches students that it can only be cosine. No. Okay? I just showed you a case where it wasn't. So, okay for constant F. But what do we do when the force changes? When we hit the brakes and the force of friction is constantly altering itself based on the speed, based on where we are, all these different things? Well, and this is terrible. This is really bad that we've gotten this far and we haven't shown you any calculus yet. You feel ripped off, don't you? That you had to take all that calculus before you took this class and we haven't shown you any calculus yet? You probably don't feel ripped off. You probably feel relieved. But, and I want you to know that even though I've dropped an integral on the screen, we're actually not going to do this integral except maybe once. Okay? We don't have time in Physics 4A to do a lot of calculus here at Fresno City College because we are required to follow the state curriculum standards, and our, meaning the law. And Fresno State has dictated what those standards are because they're our chief transfer institution. And on the books at Fresno State, they cover 19 weeks of material. Now, when you have to cover 19 weeks worth of material in 18 weeks, which is really 17 weeks because of finals week, you have to cut corners somewhere. So what we do here at City College is we cut corners on the calculus in 4A, but that's okay. We make it up to you in 4B.
Oh.
Derivatives and integrals are awesome things, but what is this one trying to say? It's telling us that we're going to take a look at a little tiny piece of work, a force times a little tiny distance. What is the force doing in that instant? And then find another instance worth of work and another instance worth of work. And even if it changes, that's okay. We can just add all those little tiny contributions of work together to find the total thing. That's really what that says right there. Okay? And this would be like from some x initial to some x final, if you're going in x. So just kind of hold that in your brain a little bit. Let me show you one example since we're here, okay? And that is the example of a spring. We're going to talk a lot about springs starting now in these chapters. We haven't done anything like this before. But when you take a spring and you stretch it, the amount of force that the spring applies to your hand does not stay the same. When the spring is in its resting state, the force is 0. When you push on it, it pushes back. If you pull on it, it pulls back. The amount of force is 0 at its resting or equilibrium state, but as you stretch the spring further and further and further, the stronger and stronger that force becomes. And that's what that statement there in the box is trying to say. That's called Hooke's law, H-O-O-K-E-S. And it's trying to tell us that the magnitude of force that a spring exerts is proportional to its stretch, where x is the amount of stretch that the spring has had. That k sitting in there is the spring constant. It tells you how strong the spring is. So like Jell-O, which is a spring, really low k's, very wiggly. Slinkies are really low k's. The springs in a trampoline are a bit stiffer, okay, bigger forces there. So larger case. The springs in the suspension of your car, those are really, really stiff because your car is really heavy. So those would have large Ks. So K is a way of capturing how strong the spring is or how stiff the spring is. You will see in your book, online, all these other places, a negative sign often dropped into this equation. And the reason for that is, if they're being careful, they would have put vectors on it. The minus sign is a reminder. It's a reminder that if you pull a spring and stretch it to the right, the direction the spring is acting, its force, is which way? The left. And if you compress it to the left, Which way does the spring push? To the right. In other words, the direction of the force applied by the spring and its stretch are always in opposition. That's what that minus sign is there for. That minus sign is never used in calculations. Physicists do this all the time. We will define something with a direction, but then drop that negative sign and draw a free body diagram instead. So, again, this is just part of your learning how to speak physics. Okay? You'll see that negative sign, but don't feel like it's an absolute, you have to include it every time. The direction of the force will be handled by a free body diagram. Okay? That's why in my way I write it, I don't write vector signs on it, the one in the box. I just write magnitude. The magnitude of the force is the spring constant times the distance. All right. That's a varying force. And if I want to find the work that a spring does, I can integrate that varying force over some distance, from some final initial to some final distance. Well, k is a constant, so where does it belong in an integral? Outside. And I'm left with the integral of x dx. Good. Yeah, no, I start yawning too when integrals get involved. And then I evaluate this, right? So this is 1/2 k x final squared minus x initial squared, right? So there, right there is the work that a spring does as it stretches from one point to another. And if our initial point is 0, oh, and by the way, for springs, you don't get to pick where 0 is. 0 is defined as the equilibrium or resting length of the spring. So if we take a spring from rest and stretch it 10 centimeters, how do we find out how much work was done? X final is 0.1 meters. X initial, 0. Spring constant. Calculate. Don't forget the squares. Now we know the work. So, integrals have their place. I showed you one.
So does that mean that work is always going to be final and not initial?
No, it goes between final and initial points. Don't get your quiz sheets out because we're kind of out of time for that. I think what I'm going to do instead is talk about one more thing and then I'll drop the quiz on you on Monday. So you can have something to look forward to over the weekend. I'm in a little bit of a derivation mood this morning. I don't know if you could tell. Just kind of feeling the math today, right? So I want to show you something. I want to bring up an old friend. Remember that one?
Yeah.
It was a nice one, wasn't it? Yeah. Was there a time when you thought this was hard? Yeah, a little bit. Yeah, man, this was hard stuff. How am I ever going to do this exam? Now you know Newton's laws. This was a time of innocence, wasn't it? A time of joy, happiness. All right, I'm going to solve this for the acceleration. And that's going to be v squared minus v naught squared over 2 delta x. Right? And then I'm going to do something bad. I'm going to bring out Newton's second law. Okay, and I'm going to insert that acceleration in that I just found, right? V squared minus v naught squared over 2 delta x. And then I'm going to move the delta x over here. I'm going to clean up a little bit. It's going to be 1/2 m v final squared minus 1/2 m v initial squared. And what's sitting on the left-hand side? Work. Force times distance. That's work, isn't it? What did we just find? By a car crash. Brain goes right to the most violent thing. The amount of work necessary to change the speed of an object. Right? we've got a final speed, we've got an initial speed. There's the amount of work. The work is the difference between these two terms. It'd be handy if we could have a name for what those terms are. What is this a difference between? It's not a difference in speed. It's not a difference in m. It's not a difference in halves. It's a change in something called kinetic energy. Kinetic energy. If we say kinetic energy is 1/2 mv squared, then kinetic energy will change when force is applied to an object and that force causes the object to move a distance d. When you are stopped at the stop sign, how much kinetic energy do you have? None. Why? It's a good day, isn't it? You can say things like, it's not moving and I'm right. No kinetic energy. Step on the gas. Are there forces propelling you forward? Yes. Did your speed change? Yes. And when you get up to 30 miles an hour, do you now have kinetic energy?
Yes.
Yes. Was work done? Yes. By what? The engine. My foot. Work was done. And when work happens, changes in energy happen. And here's the first one. Changes in kinetic energy. Now, that work term isn't going to be just changes in kinetic energy. When we come back on Monday, we're going to do changes in potential energy. But realize that one of the things we've done here is we've all just eliminated a force by hiding it in a work. And is work a vector, a scalar, or an elephant? It's a scalar. Where's the acceleration?
Not there.
It's not there. I mean, it's hiding, right?
Yeah.
There's a v, there's a difference of v's. But if you don't care what the acceleration is, if you don't care how long it takes in time, can you find the final speed of a car if you know how much work the engine does? Yes, you can. And we're going to do that on Monday, among other things, because we are going to unlock the power, pun intended, of energy.